So this is the beginning of a set of 3 lessons on Newton's laws of motion. And these are basically the laws that govern how forces work. So before we start to talk more about forces themselves, we're going to talk about Newton's laws just so we know what rules those forces have to obey. First of all, what is a force? Well, a force is a push or a pull. So anytime any object anywhere in the universe feels a push or a pull from something else, that's a force. Now we're going to want to measure forces, and forces have units that we'll use to measure them. And in the metric system, the units we use for force are called newtons. Now you'll notice that newtons here is with a capital N. Not all units have capitals at the beginning. The reason here is this is someone's name. And this unit is named after Sir Isaac Newton, this guy right over here. Now, this guy is known for developing a whole bunch of science around the idea of forces. And the story you may have heard about him is that he was sitting under an apple tree thinking about physics. Apple fell down, hit him on the head, and it gave him the idea for gravity and how it worked. Now, that story is almost certainly not true. But what we do know is he did develop a theory for the force of gravity that was revolutionary. And at the university where he worked, which was Cambridge University in England, there was a tree that he liked to spend time sitting under while he pondered his work. But the fact that an apple fell due to gravity, hit him on the head, and gave him the idea for gravity is most likely an urban legend. So a little bit of background on forces here. And I'll just backtrack 1 second here and say that, so this unit, newtons, that we use to measure forces, I want to give you a sense of roughly how much that is. Now, keeping in theme with that previous story I told you about with the apple tree, a newton is about the weight of 1 small apple. So if you take a small apple and you hold it in your hand, you have to push against gravity to stop that apple from falling, to hold it in place. And how hard you have to push to hold 1 apple up, a small apple, that's about 1 newton. So that gives you a sense of what 1 newton of force sort of feels like. Some background on forces. So there are all sorts of types of force in the universe. We'll talk about friction. We'll talk about something called the normal force. We'll talk about gravity. We'll talk about tension. We'll talk about elastics. All of these can be broken down into 4 categories. And we call these the 4 fundamental forces of nature. And the 4 fundamental forces of nature are gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Now, to give you a sense of when you might have felt these forces, pretty much every time you've ever felt a push or a pull and been aware of it, that's been a result of one of these first 2, either gravity or the electromagnetic. So the force of gravity, obviously you feel that every day, pulling you down. If you've ever walked into a wall and you felt the force from the wall pushing you backwards, that's actually a result of the electromagnetic force. If you've ever had a rope tied to you and you felt the rope pull you one way, that's actually a result of the electromagnetic force. The force that the ground exerts upwards on you to stop gravity from pulling you down to the center of the earth, that's also comes from the electromagnetic force. So most of the forces you feel in the world, if we were to zoom in and look at sort of an atomic level, they all come from the electromagnetic force or from gravity. These 2 down here, the strong nuclear force, which is also sometimes referred to as the strong interaction, this is the force that actually holds the nucleus of an atom together. In the nucleus of an atom, you have a bunch of protons packed in a tiny area, and protons like to push against one another. So the reason why atomic nuclei don't blow up from all these protons pushing each other apart is because of this thing called the strong nuclear force that holds the nucleus together. Then the weak nuclear force, which we also sometimes call the weak interaction, is a complicated force, and it has to do with the process of radioactive decay. Anyways, we're not going to think too much about these last two forces here going forward, and we even won't really focus on the electromagnetic nature of this force in this course. But we will talk a lot about gravity, and we'll talk about a lot of forces that result from the electromagnetic force. Okay, so now that we've got that little bit of background on forces out of the way, let's talk about Newton's first law. So this is the first rule that we say forces need to obey. Newton's first law you likely have heard before in some form or another. And you'll find it worded in a variety of different ways. The one I like goes like this. An object in motion stays in motion, and an object at rest stays at rest unless acted on by a net force. There. And you'll notice when I said this law, I used the word net, said unless acted on by a net force. Sometimes we also use the word resultant, unless acted on by a resultant force, or unbalanced, unless acted on by an unbalanced force. Really, you can use any three of these words, and in this situation, they're all more or less interchangeable. They all mean the same thing. Now, this law is also referred to as the law of inertia. And I think it's important to focus on this law a bit because it's not entirely intuitive. An object at rest stays at rest. That, I think, is intuitive to most people. Most people say, yep, that makes sense. If something's sitting there and you don't push on it, it's going to continue to sit there. But this first part is a little weird. An object in motion will stay in motion. We often think that to keep an object in motion, you need to keep pushing on it, right? To keep your car going down the highway, you need to keep your foot on the gas. To keep your bike moving down the road, you need to keep some force on those pedals. In those situations, the only reason you need to keep your foot on the gas or you need to keep your feet on the pedals is because you're fighting against another force, rolling resistance or air resistance, and you need to balance that out. If we were to go into space and take an object and just set it off in motion, it would continue to go forever and ever and ever. We wouldn't have to keep pushing on it. And that's really the essence of this part here. Anytime an object slows down and comes to a stop, it's because it felt a force slowing it down. If there was no force acting on it, or if all the forces acting on it were nicely balanced and canceling out, things that are moving will continue to move. That's not always obvious. Okay, so if this is called the law of inertia, what is inertia? Well, we often say that inertia is the tendency of matter to keep doing what it's doing, or to not change its motion. So this means that anything that's made of matter, which is most things you probably think of off the top of your head, want to keep the motion they currently have. If they're at rest, they want to stay at rest. If they're going 90 kilometers an hour down the highway, they want to keep going 90 kilometers an hour down the highway. And that's their preference. You can get them to do other things, but that's where you need a net force to act on them. If you want that water bottle that's sitting on your desk to change its motion and suddenly start to fly through the air, you need to exert a force on it. If you want that car that's going down the highway at 90 kilometers an hour to slow down and come to a stop to change its motion, you can do that, but you need to put a force on it. And there needs to be a net force. We'll talk more about that word in a bit. So things that are made of matter tend to keep doing what they're doing. And we can actually almost measure this. Some things really like to keep doing what they're doing. Some things, have a mild preference for it. That car has a lot of inertia. It really, really wants to keep going down the highway. And if I put you in the middle of the highway and said, okay, here's a car coming at you at 90 kilometers an hour, I want you to change its motion. That'd be a tough task for you to bring that car to a stop with your bare hands. Would be tricky because that car has a lot of inertia. That water bottle on your desk, on the other hand, doesn't have so much inertia. Yeah, it would like to keep doing what it's doing, but if you just reach out with your finger and give it a bit of a push, it'll fall over and roll away. It'll change its motion. So the car has a lot of inertia. It really wants to keep doing what it's doing, and it's hard for you to change that. The water bottle has a small amount of inertia. So what is it that's different about the car and the water bottle that make this the case? Well, it happens to be their mass, which we measure in kilograms. So we can almost kind of say that the units of inertia are kilograms. Something with a lot of mass, a lot of kilograms, will have a lot of inertia. It's hard for you to change the motion of that object. Something with a small amount of mass, a small number of kilograms, will have less inertia. It'll be easier for you to change its motion. Now, I want to use this example to get you to think about inertia a little bit more. So imagine you're racing around a track on a go-kart. What I want you to do is list 3 times when you notice your inertia. 3 points on that track, 3 things you might be doing with your go-kart where you suddenly notice, ooh, this thing has inertia. It wants to keep doing something, and I'm trying to change that. So usually the 3 things people say here are, speeding up. At the very beginning of that go-kart race, my kart is at rest. It would like to stay at rest. I want it to change its motion to actually speed up. And it's going to be difficult for me to do that. I can't just give it speed right away. It takes a while to get it going, and I'm going to have to push hard on the pedal and make the engine work hard to cause that to happen. I'm fighting the car's inertia when I'm trying to get it to speed up. Now this leads nicely into the next situation where you notice the car's inertia, and that is slowing down. When you're trying to slow the car down, it has inertia. It wants to keep going. It's not just going to magically slow down for you. You need there to be a net force on this car. And you usually get that by applying the brakes. And if you didn't apply the brakes, the car would keep doing what it's doing. It would keep that speed. Now, the third one's a little less obvious. And some of you may have had a question about this on your driver's test, if you've taken that. Turning a corner. If you're coming up to a corner in your go-kart and you just sit there, hands off the wheel, and you let the cart do its thing, the cart, because it has inertia, is going to want to keep doing what it's doing. It's going to want to keep moving in a straight line in the direction that it's going. And if you want it to turn the corner, you are going to have to make sure there's a net force on the car that pushes it around that corner. And you get that force by turning the wheels, and then there's some friction between the wheels and the ground. And that allows the car to go around the corner. But if that friction is gone, like if you hit a patch of ice or some oil, you won't be able to get that force on the car. You won't be able to make that corner. So speeding up, slowing down, and turning a corner are all situations where we notice the inertia that our go-kart has. Now, you may have started to notice that all 3 of these situations have one thing in common. These are all examples of acceleration. Remind you that whenever we have a change in velocity, that means we have acceleration. Velocity is a vector, so it has magnitude and direction. When I speed up, I'm changing the magnitude of my velocity. Maybe I'm going from 30 kilometers an hour north to 40 kilometers an hour north. When I slow down, I'm also changing the magnitude of my velocity. Say I'm going from 30 kilometers an hour north down to 20 kilometers an hour north. And when I turn a corner, I'm changing my velocity, but not because I'm changing the magnitude, because I'm changing the direction. My velocity might go from 30 kilometers an hour north to 30 kilometers an hour east after I turn a corner. So in these two cases, I'm changing the magnitude of my velocity. In this case, I'm changing the direction of my velocity. But in all three of them, I'm changing my velocity, which means I have acceleration. So the short story here is, when do you notice your inertia? Whenever you try to accelerate. Now, Newton's first law, as we worded it, is kind of a mouthful, right? Objects at rest stay at rest, and objects in motion stay in motion unless acted on by a net or unbalanced or resultant force. And I think what's more important than you remembering that order of words, although you might end up doing that inadvertently, what's more important is that you understand the concept behind Newton's first law. And even there's some intricacies to this concept that aren't necessarily grasped by that wording that we used before. So the key thing I want you to know from Newton's law is this. So if you're looking at an object or you're studying an object and you know that it has no net force acting on it, no unbalanced force, no resultant force, then Newton's first law tells us it must have constant velocity. And this arrow works both ways. So similarly, if you're looking at an object and you see it has constant velocity, right? Its velocity isn't changing, it's not accelerating, then you know that it will be experiencing no net force, or no unbalanced force, or no resultant force. So if this is true, it means this has to be true. And if this is true, it means this has to be true. That is the most important thing to remember about Newton's first law, whether or not you remember that pile of words that we introduced the law to you with. Now, let's do a couple of examples to sort of show this law in action and to help you understand the idea of net or unbalanced or resultant forces and what that actually means. In this first example, it says, imagine a book sitting on a table. Draw the book and the forces acting on it. Does it have constant velocity? So let's start with a little diagram of our book on a table. Okay, so there's my book sitting on a table. I've done the book in red, the table in blue. That'll become apparent why I've done that later on. And now we're going to draw the forces acting on this book. So what are all the pushes and pulls this book must be feeling? Well, first of all, the book is feeling gravity, pulling it down. Okay, and also, if it was just gravity pulling the book down, gravity would win, and the book would start to move down. So there's clearly something else acting on this book that's preventing gravity from winning, and that's this table. The table is supporting the book. The table is holding the book up. So the table is actually exerting a force on the book that goes up. And these forces are what I call balanced. There's one going down, one going up, but they're both about the same length, about the same strength. So this is kind of like if you had a teeter-totter with one person on each end, they both had about the same weight, that teeter-totter would be balanced. These two forces are balanced. So I would say, because the forces are balanced, this book has no unbalanced force. Every force is balanced by something else. The table force is balanced by gravity. Gravity is balanced by the table. Newton's first law tells us this book should have constant velocity. And if you indeed look at a book sitting on a table, you'll see that it has a constant velocity of 0. So in this example, I used the word unbalanced here. I said these forces were balanced. There was no unbalanced force. We can also use the word net or resultant. The word net kind of means if you take a bunch of things and add them together, what's the leftover part? We often talk about net income. That's basically the money that you get from your job minus the money that you have to send back to the government in taxes. That leftover part, and hopefully you have some money left over after that happens. That's your net income. Same thing here with forces. I've got this force kind of going up, and I've got some force over here going down. And if I allow those to kind of cancel out a bit, the net force is what I have left over. And in this case, because these two perfectly cancel out, I have nothing left over. The net force is 0. And the word resultant, you'll remember from when we worked with vectors before, just means if you take a bunch of vectors and add them together, what's the bit that's what's the leftover bit? What's the answer you get? The resultant. And if I take this arrow going up and I were to add it head to tail with this arrow going down, I'd get right back to where I started. I'd have a resultant that is 0. So when I say there's no net force, or there's no unbalanced force, or there's no resultant force acting on this book, those all mean the same thing. And Newton's first law tells us the book then must have constant velocity. So let's look at the next example. The book now falls off the table. As it falls, draw the book and the forces acting on it. Does it have constant velocity? So let's do our table again. So there's my table and there's my book beside it. So someone's taken the book from up here, they've maybe pushed it off the edge of the table, and the book is now starting to fall. As it falls, draw the book and the forces acting on it. So this book still has gravity pulling it down. It's tough to get rid of gravity. Gravity's, while you're around planet Earth, gravity's kind of always there. But now there's no table underneath the book to support it. So there's no table force going up, and the book just has this one force. So now I would say this force does not have something over here balancing it out. So this force is unbalanced, and we would say this book experiences an unbalanced force. Similarly, there is a net force here, or a resultant force. Therefore, from Newton's first law, we know that this book must have it does not have constant velocity. Because there is a net force, an unbalanced force, a resultant force, there does not need to be constant velocity. Okay, and let's do one final example. A box slides along the ground with constant velocity. Draw the forces acting on it. Okay, so there's my ground. And there's my box. So right away, okay, what forces are going to be acting on this box? Well, you're probably starting to get the hang of this by now. Gravity is going to be acting on the box, pulling the box. And just like there was a force from the table on our book supporting it, stopping it from falling, there's a force from the ground on our box, stopping it from falling. So gravity's pulling it down, but the ground is pushing it up. If this box is sliding along the ground, you might think that there's probably someone pushing it. And you'd probably be right about that. So I don't know exactly what this scenario looks like, but we could say there's maybe someone over here on this side of the box, and they've got their hand back here held onto the box, and they're dragging it behind them as they go. So we can say maybe on this side of the box, there's a force going that way. And we can call this the force from a person. Now here's where a lot of people might say they're done. right? I've got the ground holding the box up, stopping it from falling. I've got gravity pulling the box down, as it always does. And because this box is sliding along the ground, it probably means there's something pulling or pushing it. And we're saying, yeah, there's a person over here that's pulling it. But if you look at this picture, these forces are unbalanced. The ground and gravity balance each other out, but this force from the person isn't balanced with anything over here. So if I add up all the forces, I have something left over. This guy is going to be left over. This is my unbalanced force, my net force, my resultant force. So as I've drawn the box here, it would actually not have constant velocity. This box would be speeding up. So because I've told you in this example the box does have constant velocity, we know we're missing something from this picture. And also, in your own experience, you probably know that if you drag a box behind you and you're pulling on it, it doesn't just go faster and faster and faster and faster. So why is that? What have we missed from this diagram here? Well, the force that we've missed, and I'll add it right now, is friction. There's some friction between the ground and the box that's causing it to sort of slow down a bit. That is probably a full grasp of all the forces acting on this box. And we see now that this diagram does support what happened in the question. This box, as we've drawn it with these forces, would have constant velocity because the forces are balanced. Ground and gravity are balancing each other, and the force from the person and the force from friction are balancing each other. So that's the essence of Newton's first law. If you see an object that has constant velocity, you know the forces must be balanced. And if you see an object with balanced forces, you know it must have constant velocity.